This mechanics physics question contains working out speeds of an object sliding down different slopes, as we can see in figure 1 and figure 2. We also need to explain in 2.2 how the acceleration of the truck will change along a slope of varying angle. And the final part, 2.4, is a momentum explanation question. Right, so for part 1, we have a truck moving freely down a ramp, inclined at an angle to the horizontal. The truck starts from rest at the top of the ramp and reaches point A. Friction and air resistance are negligible. As the truck moves down the ramp to point A, its center of mass has a total vertical displacement of 8 meters. And we want to calculate the speed of the truck at point A. Okay, so how we would solve this question is by considering conservation of energy. The truck loses gravitational potential energy, and it gains kinetic energy. The height in this case is 8. We're trying to work out the final speed. We can cancel out the m's, move the 2 to the other side, so v will then be equal to the square root of 2gh, so that will be 2 times 9.81 times 8, and that will be 12.5 meters per second. So whenever you're using mgh, you always have to use the vertical displacement rather than the distance along, in this case, the angled slope, which we don't have anyway. And bear in mind also for this question, we can't use suvat. So to use suvat, we have to have 3 of the 5 different suvat variables in order to work out a 4th unknown. In this case, we know it starts from rest. We don't have the distance traveled along the slope itself. We only know the vertical displacement of 8 meters. We also don't have a final speed. We also don't have time. We also don't have acceleration. Acceleration you can work out from the component of weight that will be parallel to the slope. We don't have any information about that either. So for that reason we can't use suvat, and that's why I used energy conservation here instead. Figure 2 shows the truck moving down a ramp with a varying slope. The truck starts from rest and it moves freely down the ramp. It reaches point C and then moves along the horizontal runway to D. Friction and air resistance are negligible. Discuss how the acceleration of the truck in figure 2 differs from the acceleration of the truck in figure 1. Okay, so let's draw a force diagram for what we have here. So I'm just starting with the weight force. We're going to consider here the parallel component of weight to the slope. This is what determines what the acceleration will be. So this will be 90 degrees. This will be theta, let's say. This is the component of weight that is parallel to the slope. Let's call that mg cos theta. Now let's say the truck changes position. It's now further down the slope. So the component of weight parallel to the slope will change as well. So this is the same weight force, mg. The component of weight parallel is now this bit here, again mg cos theta, but as you can see from the diagram, that component has decreased. Mg cos theta has gone down. And you can see that the angle has increased. If the angle increases, that means that cos theta will decrease with it. And if you think of a cos graph, you can see why that would be the case. And this value of mg cos theta is the resultant force. There is a component of weight that is perpendicular to the slope, but that component of weight is cancelled out by the normal contact force. So you'll have a normal contact force here, that cancels out with this component of weight. And similarly, you'll have a normal contact force here, which cancels out with this component of weight. There is no friction or air resistance, and that means that the weight force parallel to the slope, mg cos theta that is, that will be the resultant force. So the resultant force will decrease as the truck slides down the slope, and if it decreases, that means the acceleration decreases with it. In this diagram, the component of weight parallel to the slope is constant, and therefore the resultant force and acceleration will be constant as well. Okay, for 2.3, the total vertical displacement of the center of mass of the truck in figure 2 is also 8 meters. So that's basically saying that the truck that we have here is 8 meters above the ground. The speed of the truck when it reaches the horizontal runway is the same as the speed of the truck in figure 1 when it reaches point A. Point A was the end of the slope. Explain why. So, the two objects have fallen the same vertical distance. When you're considering the equation, mgh is equal to a half mv squared, the h represents the height that the object has fallen through. That's the same in both scenarios, therefore we lose the same GPE, gain the same kinetic energy, and therefore the final speed will be the same in both scenarios. And for the final part, for 2.4, the horizontal runway in figure 2 has negligible friction and air resistance. As the truck moves along the runway, it starts to rain. The rain falls vertically and water collects in the truck. Discuss whether there are any changes in the momentum of the truck and collected water. So let's start with the rain droplets. I think they're a little bit easier to understand. The rain is falling vertically, so therefore the initial momentum is going to be downwards. When the rain then falls inside the truck, it will gain a horizontal momentum. There will no longer be a vertical momentum. So that should be enough for a couple of marks. So for the truck has a horizontal momentum to start with. Let's just call that P1. The water droplet doesn't have any horizontal momentum, so horizontally the momentum is 0. The initial horizontal momentum of the two, the rain droplet plus the truck, must be equal to their momentum after they combine. So when they combine, the rain is now inside the truck. The momentum of the raindrop and the truck will still be P1. So P is constant. But then the mass of the truck is increasing as it gains rain, as the rain collects in the back of it. Mass goes up, and therefore the velocity should decrease when looking at this equation. If P is constant, if mass goes up, therefore velocity must go down to keep momentum constant. And that will form the second part of our answer.